Okay, so now we finally have everything in place to understand and use Stokes Theorem for computing work. Remember the statement of Stokes Theorem, you have a surface, or let me start differently. You have a curve, a closed curve Z, and you want to compute the work done by a vector field along this curve. And what Stokes Theorem says is, find your favorite surface. That's like what's great about it. Find your favorite surface whose frontier, whose boundary is this curve. So notice in particular that all these different surfaces have the same boundary. So really I could use any of these for Stokes Theorem. And what Stokes Theorem says is that instead of doing the integral along the curve, you can do an integral along over the surface of some quantity. What is this quantity? Well, you take the curl of the vector field, which we already know how to take a curl. You take the dot product with the normal vector, the unit normal vector to the surface, and you integrate that against the area of the surface. Okay? So here are the two formulas that we will use for this example and the next one. In order to find these formulas, you need to write the surface. You need to parameterize the surface. Again, that means to write the position vector as a function of two variables, u and v. So in the case of the cylinder, for the example that I did for computing the surface area of a cylinder, the variables were theta and z, right? And so once you parameterize the surface, the normal vector, one way to compute the normal vector, there are other ways, is to take the cross product of these partial derivatives of the position vector with respect to each of the coordinates. That's a vector that's perpendicular to the surface, but you want something of unit length, and so you normalize it by dividing by the norm of that cross product. So that's what goes here, and ds is like what I explained last time. It's just the norm of this the very same cross product. This is like the area of the tiny parallelograms that we were working with. So I mean, strictly speaking, if you think about the statement of the theorem, since in a way these are always multiplied, these terms always cancel each other out. But philosophically, it's better to just write it this way. Because you can still do integrals which do not, you can still do surface integrals which do not involve this particular expression, and for those you still need to use the s with this formula. So it's better to always keep the s as it is, even though in practice this factor ends up canceling that factor. Okay. And so let's do an example where we apply Stokes theorem for doing some work. So you have the units, you have the circle of radius 3 on the xy plane, right? And so I want to compute the work of this vector field. And instead of computing the work of a vector field, I'll use a northern hemisphere as a surface whose boundary is this curve. Okay, so notice that I could have chosen other surfaces. For example, I could have chosen the disk of radius 3 on the xy plane. You can also use this one for Stokes theorem. But now what I want to use as a surface is this northern hemisphere. And so what we need to do first, like the first step for Stokes theorem, is always find r. So and usually the idea here is that we write, again, you have to think that you're going to specify any point on the surface in terms of two variables. What we want to do is use coordinate systems that we have studied in the past. So the coordinate system that's most convenient in this case is spherical coordinates, just because we're working with the northern half a sphere. So remember that in spherical coordinates, the coordinates are rho, let's see, sine of phi, cosine of theta, rho sine of phi, sine of theta, and rho cosine of theta. But if we're on the sphere of radius 3, right, this has equation x squared plus y squared plus c squared equals 9. That's the equation of the sphere. And so when you write this in polar coordinates, this becomes rho equals 3. So rho equals 3 on the sphere. And so that means that any point on the sphere, x, y, z, is of the form 3 sine of phi cosine of theta, 3 sine of phi sine of theta, and 3 cosine of theta. And so notice that what I'm saying is that really to specify any point on the surface of the sphere, you just need to know the angles phi and theta, because like the radius is fixed, so it's not information that's changing. That's the point of a parameterization. On a parameterization, you only keep track of the information that can change from point to point on the surface. All the points on the surface have the same value of rho, so that's why you don't need to think of it as an extra parameter or variable. So what I'm saying is that there's this parameterization for the sphere, which is 3 sine of phi cosine of theta, 3 sine of phi sine of theta, 3 cosine of theta. Now, strictly speaking, to any surface, even if you're working with unit vectors as we had discussed in the past, there's really two like normal unit vectors, because you could choose this one or you could reverse the arrows. There's a way to decide, I'll say this in a moment, but there's a way to decide which normal vector you want to use, so in Stokes Theorem, so that this works correctly, because notice that this involves like something that's like a cross product, so there's like a right hand rule associated to it. In practice, that takes some use, takes some time to get used to it, so I'll always tell you which normal vector you should use. So I'll make this more clear in a second, but that is not something you have to worry about. So in order to find the normal vector and everything else, we have to compute first these partial derivatives. These are with respect to the parameters, so let's differentiate this first with respect to theta, and you get minus 3 sine of phi sine of theta, 3 sine of phi cosine, oh sorry, this should have been mistake, crisis averted, prevented, but almost good. Sorry about that. Yeah, now this is correct. Sorry, I was saying 3 sine of phi cosine of theta, and this is 0. Okay? And then the partial derivative of r with respect to phi equals 3 cosine of phi cosine of theta, 3 cosine of phi sine of theta, and then minus 3 sine of phi. And so the normal vector involves the cross product of these two. So let's do the cross product. This is a messy cross product, but we have to do it eventually. Okay, so we're going to do that cross product, and what do we get? We get you get -9 sine square of c cosine of theta. Good, that gives you 0. And then you get so this one, and then that one. Okay, yeah, you get -9. Yeah, sine square of phi, sine of theta. Remember, it goes plus minus plus. That's why you have to be. It's a bit tricky, this stuff with the sign. So, and then gives you -9 cosine. Let's see. And then sine. Okay, sine squared. Sine squared. Okay, yeah. -9 sine of phi cosine of phi sine square of phi, sorry, sine square of theta minus 9 sine of phi cosine of phi cosine square of theta. That's all of this is in the third entry. So you can simplify this a little bit. Because here you can factorize sine phi cosine phi, and then you get -9 of that, and then you get sine squared plus cosine squared, so you get -9 sine phi cosine phi. Okay, and let me just see this for a moment. Yeah, I think this is going to be okay, but it shows you that it is a bit messy. And here, I mean, this is strictly speaking not still the unit vector because we have to normalize it. But that's a cross product, a bit of a mess. And then the norm of that, this is all asterisk. So the norm of that would be the square root of what? Of 81 sine to the 4 of phi cosine square of theta plus 81 sine to the 4 of phi sine square of theta plus 81 sine square of phi cosine square of phi. So good. So notice that you can combine the first two, and you can take the 81 as a 9, and so you get sine to the 4 of phi plus sine square cosine square of phi, and you can pull out a sine squared. It comes out of the square root as 9 sine of phi, and then you just get sine square of phi plus cosine square of phi. So this norm is just 9 sine of phi. So this is pretty cool. So that norm is that thing, and then actually the norm is really all that we cared about. So, and the normal vector. So we can erase this already. So the unit normal vector is asterisk divided by the norm of asterisk. So Okay, I have to remember which was the vector field, but I'll check it on my iPad in a second. So you're dividing this by 9's go away everywhere, and then you're dividing by sine of phi, so you get negative sine of phi cosine of theta, negative sine of phi sine of theta, and then you get negative cosine of phi. Okay, and so this is a actual normal vector, but notice that at the north pole, so the north pole is characterized by say phi being equal to 0. So when phi equals 0, this goes away, and this gives you negative 1. So it's pointing inwards, right? And so, again, you don't need to worry about this, but in the problem, in the statement, I would actually say use the normal vector that's pointing outwards, away from the sphere at the north pole. And so that means that you have to use, and this is again because there's a convention involving Stokes Theorem, but so you have to use the minus n so that it points away from the surface. So what we found, let's put these two pieces together of information. So we have the ds, this is all that we need. So we know that ds is the norm times du dv. So this is the norm times du dv, which I mean it's either d phi d theta or it doesn't matter in which order you write this. So this is ds. And the normal vector, again, in principle you could have thought about using this one, but you have to use the other one. But that's something that I'll tell you which one to use, so you don't have to worry too much about it. Okay? We're almost there, but again, notice that this is a complicated example. Now we have to compute the curl. Okay, thankfully the curl won't be too bad. F was this vector field. Oh good, yeah, this is not that terrible. So F was a vector field, the curl of F is this. So this gives you 0, 0. Oh good, yeah, it's not too bad. And then negative 2. So what finally Stokes Theorem says is that the work by Stokes, the work, which is this is the other notation for work, is just the integral over the surface of the curl, which is 0, 0, negative 2 dot, and I won't write all of n now because notice that the only thing that survives is the third entry times the s. So this gives us what? Again, this will be a double integral of what? It's minus 2 times, so you get minus 2 cosine of phi. That's the only thing that survives from that dot product. ds is 9 sine of phi d phi d theta. And then you have to figure out the bounds for the northern hemisphere. So theta can go from 0 to 2 pi, and phi goes from 0 to pi over 4 in this case. Good, and now we're finally ready to compute this quantity, and it gives us it gives you negative 18, the integral from 0 to 2 pi, the integral from 0 to pi over 4 of sine of phi cosine of phi d phi d theta. Again, there's nothing involving theta inside, so you can just do the exterior integral already, and this gives you negative 36 pi, integral from 0 to pi over 4 of sine of phi cosine of phi d phi. And again, you can make a substitution like u equals sine of phi, and this gives you sine square of phi over 2. Yeah. Evaluated when phi equals pi over 4 and phi equals 0. At 0 you don't have to worry because this is sine, and so you get minus 36 pi times, minus 18 pi times sine of pi over 4 is 1 over root of 2 squared, and so that gives you 1/2, and so you get negative 9 pi. So according to Stokes theorem, the integral gives you negative 9 pi. And so you can do the integral directly to verify that that's the case. Tiny correction, the bounds are from, the entire phi goes from 0 to pi, so when you have the hemispheres from 0 to pi over 2. And the integral now is correct.